Alright, so sizing one-way slabs and beams in concrete. So this would be the beam and girder system that we're talking about here. So, ACI 318, which is the guideline for designing elements in concrete, gives us these minimum thickness tables for slabs and for beams given a span. And note here for the slab table that we have a caveat for fire rating resistance, which we talked about earlier. So if we're using normal weight concrete, we have a limitation to use at least a 4.5-inch slab, or if we have lightweight concrete, we need the slab thickness to be at least 3.25 inches minimum. So now that we have these tables, let's go ahead and look at an example of sizing some slabs and beams for a one-way system. So given a building that looks like this, with a typical bay sized 30 foot by 15 foot, let's size a slab and a beam for this system. And note that we are designing a one-way system for this example. And so the load is going to travel the shorter direction along the slab. So the span for the slab is going to be 15 feet. And for the beams here, it's going to be 30 feet. And note that in this example, we don't actually have any intermediary beams. If we did, then the shorter direction for the slab to span would actually be east to west between the beams. But in this case, we are going to design the slab to span the 15 feet on its own. And we are only going to provide east-west beams between the columns. Now, recall how earlier we talked about simply supported elements versus continuous elements. And you'll note in this table that we have different support conditions. We have simply supported, one end continuous, both ends continuous, and cantilever. And the type of condition that we have will change our span to depth ratio, ultimately affecting the size of our elements. So, if we consider our slab, if we look at this interior bay, we will see that the slab is continuous over these two supports. And so we would be able to use this both ends continuous column when designing this interior bay. However, if we were to look at an exterior bay, like this one here, we would see that the slab is continuous over this beam on this side, but it is not continuous on this side. And so we would have to use this one end continuous row. Similarly for the beams, if we were looking at an interior bay, the beam would be continuous over the column here and continuous over this column here. And so for sizing this beam on the interior bay, we could use the both ends continuous support condition. However, if we were to look at something on the exterior, we would see that, for example, this beam would be continuous over this support, but it would not be continuous over this support. And so we would have to use the one end continuous support condition. And note how, as we move from the both ends continuous condition to the simply supported condition, our depth will increase, as we discussed earlier. So our largest members will be the ones on the exterior, the ones that do not have continuous supports on both sides. So, let's just say that we want to be conservative here and design the entire building floor plate for the worst case scenario, which would be one of these corner bays. So let's select this corner bay to design our elements. So for the slab, we are continuous on this side, but not on this side. And so we need this one end continuous L/24. So 15 feet times 12 inches per foot over 24 will give us a 7.5 inch slab. And for the beam, we will again have continuity over this support on this side, but we do not have continuity over the support on the left side. And so we will need to use this L/18.5. So 30 feet convert to inches divided by 18.5 will give us a depth of approximately 20 inches. And note that typically for beams and girders we want to round up to whole dimensions in concrete. Also note that the slab and the beam are cast monolithically, and so the total structural depth is not going to be 20 inches plus 7.5, but rather the slab will be 7.5 inches and the total depth of the beam will be 20 inches measured from the top of the slab. And so the total structural depth is just 20 inches. And so that is how we size slabs and beams for a one-way concrete system. To be conservative and for the sake of uniformity across the entire system, we will typically select one of these exterior bays and use these conditions here to size our elements. Now let's move on to sizing two-way elements. And note that for something to be truly two-way, we need the longer dimension divided by the shorter dimension to be less than or equal to 1.5. If we start to have a really long dimension in one direction and a really short direction in the other, the slab isn't really going to be able to transfer load in this long direction very easily. And the majority of the load is just going to travel the short direction. And we'll end up with a one-way system. So ideally for two-way systems, we want something that is square. That is, where L1 is equal to L2. And so we have the same amount of load traveling north-south that we do east-west. And actually the same minimum requirements apply to beams in one-way and two-way systems. And so we're going to use this same chart up here for one-way or two-way. However, for two-way slabs, we do have a much different table. And it looks like this. And note that once again we have our 2-hour fire rating requirements. So we can never be less than 4.5 inches or 3.25 inches, depending on whether we're using normal weight or lightweight concrete. Now, this chart can look a little complicated, so I'm going to do my best to simplify it for you guys. First of all, we are rarely ever going to use rebar with a strength less than 60 KSI, which is this column here. This column is the strength of the rebar. Also, we typically don't use this 75 KSI rebar. 60 KSI is what is typical, and so we're only going to focus on this row here. Also, these next two columns where it says without drop panels or with drop panels, recall that that means the difference between a flat plate and a flat slab. And a drop panel looks like this. Basically just an extra bit of thickness added to the slab over top of a column. So if you see drop panels, you use the right side of the chart. If you do not, you want to use the left side. And as we had before, with continuous support conditions, or with continuous on one side, or simply supported, we have interior panels versus exterior panels. And if we want to be uniform across the entire plate, we're going to want to design for the worst case condition, which is the exterior panel condition. Which brings us to the last bit of information that we need to know about this chart, which is whether or not we have edge beams. And edge beams are just exactly what you would expect. They are beams that go around the perimeter of the building. So on the left here, I've drawn an example of a plan view without edge beams, and on the right, an example with edge beams. So you can see that if you provide edge beams around the perimeter of the building, you can actually slightly decrease the thickness of the slab. So let's look at an example of sizing the thickness of a slab with drop panels and no edge beams. So first of all, note that we have an L1 over L2 equal to 30 over 20, which reduces to 1.5. So this slab can in fact act as a two-way system. And when we size the slab, note that we want to take the clear span in the long direction when we size two-way systems. So here we are taking the long span, which is equal to 30 feet. And in this example, we have drop panels, but we do not have edge beams. So looking at our chart, we have drop panels, but we do not have edge beams. And we're going to be looking at an exterior panel so that we can get our maximum depth. And so we will be using this long span divided by 33 criteria. So take our long span, convert to inches, and divide by 33. And that will give us a slab thickness of 11 inches. And note that in this case, we do not have any interior beams. And so our total structural depth, aside from the locations where we have these drop panels, will be 11 inches. So now that we have sized a few concrete elements, let's look back at our structural material performance matrix. And this time, we will add in concrete to the discussion. And note here how concrete especially shines in the places where steel did not, and vice versa. So concrete performs well for large loads and achieving shallow structural depths, vibration control, fire resistance, environmental resistance, architectural freedom in a couple different categories. However, it falls short in cases where we need to come back and reinforce the structure, as well as minimizing dead loads on the foundation. And so it's important to keep these different design criteria in mind when we're selecting a material for our structural system for our building. Now in the next video, we are going to be talking about foundation systems. And after we wrap up that discussion, that will conclude the lecture for this week.